Hi folks, in this video we're going to be looking at integration. Specifically, we're trying to understand how we calculate the definite and indefinite integrals of functions so we can use them to solve certain physics problems. A big disclaimer here is I am not going to explain to you why integration works. I am not going to even help you do it for arbitrary functions that are sort of interesting. That is what your calculus class will do. And, you can apologize to your calculus teacher for me for just teaching you the down and dirty way to do some integrals. In fact, at the end of all of this, I'll say you probably don't even need to know even this much if you can use the reference sheet effectively. So remember, for us, integration is a tool. In math, it is, of course, a useful thing, but it is also something that is worthy of figuring out and understanding. And I once did. But because I studied physics and not math, I don't fully understand the why of integrals anymore. Yeah. Okay. So we start with derivatives. And so by this point, you've all sort of learned about derivatives a little bit in your calculus class. And essentially for us, they are the slope of a tangent line of a graph, right? They tell us the instantaneous rate of change, how fast something is changing right now. It might be with respect to time, it might be with respect to position, as we get with different things. But ultimately, it is the slope of that function at that point, right? If we have something like this, the velocity, which is the derivative of the position with respect to time. The acceleration is the derivative of the velocity with respect to time. And as we learned in the last video you watched, the force that is involved in a potential energy and storing potential energy can be found by taking the negative of the potential energy's derivative with respect to position. Those are those potential energy curves. They also let us do things like finding minima and maxima by taking a derivative and setting it equal to 0. This will show us the local min and max, those turning points. Those equilibrium points, which we were also looking at last time. Wherever those equal 0. And then we get to another type of thing we do with graphs, and that is finding area under the curve. We've used this already. We've done it with simple shapes of curves, things that were horizontal. I forgot to change this, but for yourself, pause the video maybe, and think about three different ways we viewed area under the curve. You probably remember that we've done displacement from a velocity profile, right? Delta x is v, delta t. We've also done work done by a spring. We've also done the change in velocity. Right, we've done all of those things. And that was how we kind of backed in, if you will, into integration without actually doing the integration. It's pretty easy if you've got linear functions, right? They make nice geometric shapes. They make triangles, trapezoids, rectangles, what have you. Pretty easy to do these areas, even if it's, individual little pieces that you put together. There's a positive delta x, there's a negative delta x, and so on. But when a function is a different shape, you could break it into little geometric shapes to try to approximate it. And in fact, oftentimes that's what we do for numerical integration if we don't have an exact function. But if we know the function of that curve, there's an easier way to do it, and that is to use integration to find the area under that curve. So when do we need to integrate? In Unit 4 right now, work and energy, that's an integral technically. We've only done it in its discrete form, but we will look at that as well. In our next unit, we'll find the center of mass by using integration. And we'll use it in the impulse momentum theorem, which is similar to the work energy relationship, but with impulse and momentum instead of work and energy. In Unit 6, we use it to find rotational inertia. And these are, summing things up. Just kind of fun. So let's go back, all the way back to the beginning of the year. If you throw an object straight up in the air, right, and you have a position time graph that looks like this, right, curved. The slope of it is taking the derivative, and we get a velocity time graph that looks like this. And then we do that again, and we get the acceleration. On the other side, we could do the area under the curve. You start with the area is the acceleration is dv dt. But then if you go from that, you can find a change in velocity by talking about the average acceleration times delta t, and similarly to find the delta x. Integration is basically, for our purposes here, the antiderivative. It is the inverse function of what we are doing to get a derivative. So an area is an integral, right? We integrate the acceleration with respect to time to get the velocity at a particular point. We integrate the velocity with respect to time at a particular and evaluate it at a particular point to find the position at a particular point. So the other thing we're missing, though, is I may be able to get x was a function of time by doing this, but without the initial condition, I don't have all of my information. And so that's one of the things that we have to kind of add in. The third idea behind integration, the idea behind integration that we really care about here is that you can estimate areas under the curves by drawing these little rectangles and making them smaller and smaller and smaller, right? And add up all the little rectangles. And that's essentially what we're doing. We're doing a sum that is no longer discrete chunks. It is a continuous sum where the delta x becomes arbitrarily small, right? If it's a rectangle, you just multiply height times base, and then you add up all the rectangles. So that's, say, for a force versus position graph, the force is a function of position times a little bit of delta x. And how do we make it more accurate? Well, we keep shrinking that delta x as small as it'll go, making those rectangles thinner. And then we think of the limit as those rectangles become as small as they possibly can, and that becomes the integral. So the height of our curve is the f as a function of x, and the base of our rectangle is the dx, an arbitrarily small width of the base. And this is how we actually find our, our work done by a force in this case. So dx is the width of each infinitesimally thin rectangle. I remember one of my calculus professors or math professors always used to say that infinitesimally thin was an awkward word to say, and he liked to call it arbitrarily thin, which I kind of like too, because it's so small, it's completely arbitrary. So there you go. Integration, then, is really, for our purposes, adding up all these little bits in a continuous way where we no longer have to worry about the actual width, and we follow some interesting rules to get there. So today we're going to integrate, and in this video we're going to integrate by understanding that it's the antiderivative or the backwards derivative. You'll learn more about why in math. Okay, so how do we find the derivative? There's a couple of different rules. If the function follows this form, that it's a function, a force with respect to position, like the spring force, and it goes like ax to the n. So some constant times some variable raised to a power. The derivative of it, right, f prime, if you will, is going to be you drop that exponent out in front, and then the new exponent is to n minus 1. To integrate, we kind of do the opposite. If you integrate a times x to the n with respect to x, the a still survives, and we now go n plus 1, and we divide by that n plus 1. So here's an example. The acceleration as a function of time is 36t squared. The velocity as a function of time should be the integral of a dt, so 36t squared dt. And that becomes 36t cubed over 3, and we can simplify it. Now, I added an extra c there. And that's because, as we recall, when we go from acceleration to velocity, we don't fully know the initial condition without having an extra piece of information. We don't know where we start. But we can always check this to see if it makes sense by taking the derivative. So if I have the velocity is 12t cubed, and I take the derivative, we'll just assume c, the constant, is 0 for now. It actually doesn't matter. We take that, and we integrate, and we get 3t to the fourth plus c, right? Again, a constant of integration, right? You can check it by taking the derivative. You get 3 times 4, t cubed. So if the function contains multiple terms, you just do each one separately. Right? So you integrate the ax squared and the bx separately, and then you put it all together and add a constant at the end. If you have trig functions, they follow their own special rules, but the integral of cosine theta with respect to theta is sine theta plus a constant. The integral of sine theta with respect to theta is the negative of cosine theta plus a constant. And we can, again, take the derivative to check them by using our rules for derivatives. So how do we do this? There's a bunch of practice that you can do. All of these kinds of problems that we can do. And you should do as many of them as you need to make sure you're comfortable with doing these. So let's talk a little bit about this constant of integration, because in calculus, it can seem a little bit arbitrary, but I think it's really helpful to think about physical reality. If you imagine that this is your position time graph, x equals 1/2 t, right? T squared, right? So this is similar to, a free fall equation where we would say delta y equals 1/2 at squared or gt squared. But we'll just simplify it for now. There's a part of a parabola starting at 0 going out in time. Well, 1/2 t squared plus 2 and 1/2 t squared plus 4 all have the same derivative, right? So if you start with that velocity and you want to integrate to get to position, you don't actually know which one of those it will be without figuring out the starting point, right? Does it start at 0, at 2, or at 4 meters? And so we need that initial condition, sometimes called the side condition, to figure what it is. So if I tell you, oh, this object started at a position of 4 meters, then you know, oh, it's line 3. We now have the constant of integration added. When t equals 0, x should be 4. Graph 1 has a constant of integration of 0, graph 2 has a constant of integration of 2, and graph 3 has a constant of integration of 4. So if this is our integrand, and this is our side condition, then we can integrate integral of 4t with respect to t, 2t squared plus the constant, by the condition, and you get 8. Excuse me, 8 equals 2 times 3 squared plus c. You can solve for c, which is negative 10. And you can say, oh, my actual result is x as a function of time is 2t squared minus 10. So you can try this. There's a bunch of examples on page 35 in your packet as well. These were all what we call indefinite integrals, right? And that's perfectly fine for something like this, right? The area under this curve, 1/2 kx squared. We know that the force is 0 when there's 0 displacement, and so the constant of integration is 0, and we don't really have to worry too much about it. We can plug in a value for x and solve for the area, right? If I plug that in there. But this assumes that the initial x was indeed 0, that was the condition. And that's okay for a spring where we know equilibrium is at 0. But the definite integral lets us find any portion of the area. It doesn't have to start at 0 and go to the end. And this is something that I think got brought up when we were talking about spring potential energy, that you needed to calculate it at 2 points and subtract it if you wanted to know the work to go from one position to another. And this is sort of the justification for why. If I'm only interested in stretching it from x initial to x final, and that doesn't involve the 0, well, this area is not the area of a triangle. I can't just say that's equal to 1/2 kx squared. I need to think of this as the limits of integration, how much of the area I'm actually interested in. So how do we find that area? Well, the area from 0 to x final minus the area from 0 to x initial would be a way to think about it. Take those two triangles and subtract them. Practically, from an integration standpoint, in order to do this, we're basically computing two integrals. Or maybe more precisely, what we're doing is we're integrating from one place to another. So how do we do that? Well, we put in limits of integration. And we say it's going from down at the bottom, x initial, to at the top, x final. So for example, how much work is done to stretch a spring from 10 to 20 centimeters if the spring constant is 200 newtons per meter? Well, we've got our work is the integral from x initial to x final of f as a function of x dx. All right, we plug that in. And this is how we write it. We write it at the end with a kind of a square bracket, a single one, saying we're going to evaluate it there. And the way we do it is we do the final minus the initial. So we do 1/2 of 200 times 0.2 squared minus 1/2 times 200 times 0.1 squared. And that gives us 4 joules minus 1 joule, 3 joules of work done to go from x initial to x final. Here's another example. This one going back to kinematics. If the velocity is equal to 6t squared, right? I want to find how much the position changed from 3 to 6 seconds. Now, of course, I could, do the indefinite integral, and I could solve for this at t time 3 seconds and time 6 seconds and then subtract them. But if we do this as a definite integral, we can do it all in one piece. So the integral of 6t dt is 2t cubed and evaluated from 3 to 6. So evaluated at 6 and subtract what it is at 3, and we end up with 378 meters. This does bring up the question, why have I stopped worrying about the constant of integration? Well, the reason for that is if you put it in, it's going to be in both places, right? And it will disappear when you subtract one from the other. So there's a bunch more practice here. And again, I would recommend that you practice as much as you need to get comfortable with this. We will do the specifics of how we use it in terms of work and energy and center of mass and all that. But you want to be able to compute these yourself. It turns out that if you look at the equation sheet, which I think you should all have a copy of on paper, but if you go to the College Board site and say, what are my constants and my equations that I get? All of this calculus is given to you, right? It gives you the basic chain rule. It gives you the power rule. It gives you sines and cosines for integrals and derivatives in case you forget how to do it. Now, you still need to know how to do it because just looking at this may not be enough. But this is really all you need to be able to do physics. There's this video on called The Mechanical Universe that I highly recommend. If you want to learn more about sort of integration and how it behaves and stuff, which is pretty fun, but certainly an optional video. All right. As we finish this up, I want to remind you that what I have told you about integration is really just as fast and quick as I can explain why we use integration, how we use integration in this physics course. Of course, for those of you who've already taken calculus, much of this will probably be boring. And for those of you who are in calculus, it will be just scratching the surface and not really explaining a lot of the detail. So talk to your math teacher for more.